Alright, time for another draftphysics.com, debatephysics.com, also video presentation. So the Brozo still has not made his new version of his previous 2 year ago, 3 year ago experiment, where he attempts to demonstrate kinetic energy being conserved in a lever experiment, which I'm, of course, arguing is impossible if you put different masses on the lever. Now, obviously, if you have the two mass here and a two mass here and the same distance, then yes, your fake number will be conserved, your fake amount of kinetic energy. But, as soon as you change the mass, no hope. Okay, the differential becomes extreme with just a 2 to 1. It's a 2 to 1 difference, which is a gigantic difference. So, but yes, so nothing. All right. And I guess I'll draw it. So I'll pause to do that. Just start drawing. Might as well pause. All right. As seen previously, he did the experiment in this fashion. So he had a spring that he was actually compressing. And so he pulls the lever back at this end and launches the objects. So the two mass ended up going 19 frames before it reached a given distance. And presumably the distance is short enough that the difference in velocity hasn't changed their velocity much. There's going to be a dramatic difference in how far these two objects will roll. Something going half the velocity, something going one velocity rolls 1 unit of distance, something going 2 velocity will roll 4 units of distance because of the way gravity imposes friction. But anyway, so it was 19 to 11, okay, close to a 2 to 1 relationship, very far from a 10 to 14 type relationship. So anyway, he's going to redo this experiment, and so far, he hasn't provided his new proof. But anyway, so the theory of the experiment is sort of interesting. Now, you'd argue that you pull this back to a certain set distance, that this energy is the same no matter what you do. Okay, you're going to produce the energy from the spring. But the catch is, the faster the whole lever moves, that means the more you have to subtract for the lever. Okay, it's going to consume some amount of the energy. So the faster the whole lever moves, the more energy it's using to cause the velocity. And the slower it moves, the less energy it's taking from the experiment. So these are, you could argue, ideal locations where you obey the law of the lever. But if you disobey it, you'll get close to the same results. Okay, not the same, because you're losing or gaining energy by how much you've given to the lever. But for example, if I did put the one mass at the same location as the two mass, it's still going to go substantially faster. It's just not going to go twice as fast, because the lever itself will be going much faster to be able to release its energy into the object. The whole lever will have to go much faster to increase the velocity of the one mass. And if I put it out a little further, then we get into an argument again about how, it'll be much better. So the further out I put it, ideally speaking, I'm making the lever move less, so I should be able to get even more velocity, a little bit more. So instead of being too close in, you want to be too far out. So if you're going to make an error in your measurement, you want to make sure your error's out, not in, for the light mass, and in and not out for the heavy mass, because that'll change how much energy the lever has to steal from the experiment. So it is just an interesting fact. Now, applying this to Dispar, who's also continuing to make assertions. So his latest video is so bad, I really can't even explain how, I can, but I don't want to go to all the trouble. So the experiment's it starts here. Okay, here's a point parallel with the camera, and that's where the experiment starts. And the experiment's going to end up being out here. okay, and way out here. And so you can see your camera view, if you had to look up that way, you're going to be able to see something that arcs a little bit easier. It's going to look very close. But something that arcs further is going to automatically be much further away. So there's going to be a huge amount of parallax. One experiment is going to look like it happened much closer to the camera than the other experiment happened to the camera, even though you started with the same distance from the launching point. So having two launching points and having very different arcs means you can't do that. You're not going to get an accurate measurement. So if you want to do the experiment right by trying to see how much distance it actually travels, then you have to really film this in one experiment and then film from this location over here, put that in the center of the camera, and then the highest location directly in line with that and a ruler, and then you get accurate results. But he didn't bother doing that. Now, what occurred to me to solve all this, keeping in mind that these distances are kind of important. So this experiment involves a rubber band being stretched rather than a spring, and so you're pulling the lever back this way, and this is a rubber band, and you're going to launch the objects. Now, what he has is a timing gate, electronic timing gate, and he could put that over some flag on the end of the lever. And technically, right, if he gets these locations correct, that is, if he gets this one distance and then two distances fairly accurate. Here's the fulcrum. All right, which I didn't draw very accurate, but you'll get it. Then you can just measure how fast the lever moves, because technically it should move exactly the same speed to be twice the velocity here and 1 unit of velocity here. So those things should produce exactly the same. So a 1 mass, okay, going 2v, and a 2 mass going 1v in these locations, obeying the law of the lever, means the lever itself moved exactly the same speed. And so that he could measure electronically and get a fairly accurate number for how fast the lever moves through the timing gate at its maximum velocity, presumably at the end of its travel through the experiment. Probably shouldn't matter, beginning or end. It shouldn't matter where, technically, because the lever is going to accelerate at exactly the same rate. This will accelerate as if there was a 2 mass here, even though there's a 1 mass here. And when there's a 2 mass here, this part of the lever is going to accelerate as if there was a 1 mass there, and there isn't. So if he gets anything like the same speed for the lever, that would prove the 1 mass did in fact go twice as fast as the 2 mass did. So it's a way of verifying the results, the visual results, by, as long as, again, you have these distances correct. Because if you change the distances, well, then the speed of the lever will change. So it won't be of much value. So with that condition of precise measurement of distances, it should come out pretty close. All right, now, there isn't enough, of anything new to report on. There hasn't been any comments, hasn't been any references to any counter arguments to the critiques I have provided. I don't think, well, I'll check Gosling's channel, but he is conceding basically the points I made in the previous video, at least the one point, that if you change how far away the weight is from the lever itself, you will change the way the lever balances, how much energy will be put into it. So we'll go check that, and I'll be back. All right, so there haven't been any, there wasn't any comments on the subject, frankly, And there haven't been any new comments. And basically, the argument was what I pointed out was if you want to be fair to the experiment, you have to make this bar, the bar that's on the mass that's further out, longer, and then you will create a more even experimental comparison. And that's what he found, is that it moves much quicker. Okay, if he extends the distance, the weight is perpendicular to the lever. So he has it fixed so it can't move, so it's always perpendicular. So the lever is going this way, he has another bar attached this way, and then he has the same bar on the other side, except the masses are different and they're different distances, so the bars themselves have to be different lengths to be even and fair. And the point is basically it's just saying you're increasing how much lighter the object gets when it goes down. It gets very light, and when it goes up it's getting heavier because you're basically extending its distance on the lever. So you're increasing how dramatic the difference is between the lightest it is and the heaviest it is, and that's the energy that's oscillating the lever. So as you increase the energy that's oscillating the lever, obviously the lever moves quicker through its oscillating. All right. So that isn't a huge surprise, and it's pretty much as I pointed out in my video, and he pretends that didn't happen. So I'm just pointing out for reference. Yes, that's exactly how it happened. I pointed out a criticism. I pointed out how you're being unfair to the experiment, and I was 100% correct in what I stated. So you people are pathetic. All right, so to throw in something else to just fill this video, Bruce Yeany, who has he's acknowledged the receipt of the emails. So he's the only one who acknowledged the existence of this desire for people to see experiments involving kinetic energy and the proof of its reality. And it's just ironic that his newest video is exactly, it says like it's going to get to the subject. Now he uses this term Tweety boppers. I mean, everything is designed for kids because he's a teacher, so he thinks everybody's 11 years old, and it's really irritating. Anyway, inertia, center of gravity, harmonic motion, and he could say momentum and balance, because that's all he's creating, is a levered balance. And he's got the weights below the fulcrum, which means it'll be very stable in terms of whatever energy you put in. It's basically going to be the same argument, that it's just the energy you're creating with that length of lever in another direction. This is essentially the same as a straight lever with the objects suspended rigidly, so it's almost a duplicate of Gosling's experiment, except in a flexible form, which makes it even better for these type of experiments, where he could just bend this and change the position of the mass, obeying the law of the lever, and balance a 2 mass and a 1 mass, and then demonstrate this idea of inertia, whatever that's supposed to mean, in terms of the fact that somehow it's harder to push lighter objects at higher velocities, which is the foundation of their theory, which is nonsense. And again, it goes all the way back to the Leibnizian theory that 4 pounds dropped 1 foot is the same energy, impact energy, as 1 pound dropped 4 feet, when 1 pound dropped 4 feet only has twice the velocity and therefore only half the momentum. So it can't possibly do the same work. Now this does relate to the Veritasium video that I want to do in a sense, because he has the example of a spaceman throwing a tennis ball or something, some kind of ball, some sort of mass. And it's just, again, they just avoid the real subject, which is, well, what does the space guy get in return? Does he get the kinetic energy that the object has? Does he get an equal and opposite reaction in kinetic energy? No. He only gets an equal and opposite reaction in momentum. So only momentum does work on the astronaut. So how can it be stated that kinetic energy is defined as being able to do work when it can't do any work on a ballistic pendulum or an astronaut or a spaceship? It can't do work. It never does any work. It doesn't work if he crashes wooden blocks into each other. There's no evidence. I can crash a wooden block with 4 times the kinetic energy into another wooden block with 1/4 the kinetic energy, and there'll be no evidence that the one with 4 times the energy does 4 times the work. There's no evidence that it will win if those two things have the same momentum. So it's momentum that decides where you get work done. Momentum does work in the universe. Kinetic energy doesn't. So by definition, the default statement should be, if you're going to describe what energy is in the universe, the default statement really should be the one that does work, and momentum always proves itself capable of doing work, and kinetic energy always proves itself incapable of doing anything called work. And that's a really important subject, and these Tweety bloopers, ploppers, not even close. Will they come to this? They won't concede the actual subject here, that there can't be 2 kinds of energy. There's only one of these things that can actually do work in the universe, and it should be conceded by reasonable people that obviously it's momentum that reliably does work, and kinetic energy doesn't do it. It certainly doesn't do it reliably, if at all. I mean, I would argue there's no example of it ever doing any work. That there is actually ever any collectible thing called kinetic energy over and above the momentum of an object. That you'll never collect more from that object than its momentum, and that's all you'll ever collect. It's probably enough of a statement. So again, maybe I'll play with it. This simplicity is very good. I mean, it's nice to have something very simple. Certainly it's easy enough to put energy into something like this. I mean, actually it has its speed.
Well, an object in motion is going to stay in motion unless a force acts.
So he's talking about subjects that really, they aren't really related to what he's really demonstrating, which is it's just mass and velocity. And the two things remain balanced as long as the same mv is involved, and that he can in fact change the relationship by putting a lighter mass further a longer distance, and a heavier mass a shorter distance. All right, and they will produce the same. They will have the same inertia need to be supplied energy, and they will produce the same inertia energy out. Okay. Yeah. Take a pause and see if there's anything else. Alright, so I guess that'll be enough for this video. So till the next time, and such and so forth and whatnot.